Okay, thanks. Okay, welcome everybody. My name is Sameh Gabriel. I am with Intel Labs. And today I will be talking about a new library that went out with DPDK 1711. It's called the membership library. So this is not only my work. It has been a work of a lot of people, including these guys on the slide, Charlie, Yipin, and Ren, who are in my team, and then John and Pablo from the DPDK engineering team. Okay. So what is the agenda for today? So my target for today's presentation are only two things. First is to give you an idea about the membership library, what it is used for, a lot of usages on the slides. And the second thing is, if your app, your VNF is happen to be using any functionality that this membership library provide, I guarantee you that if you use it, you will get a good performance. So these are the only two things I want to come out from this presentation. So for the agenda today, I will give an overview of the library, some of the usages, a very short introduction for the API overview, and as a proof of how good this library is, I will present some results that we have a research POC with OVS showing the gain when using this library. And I have to go back to click. So what is this library all about? So this example is to show what membership and what membership test is, and the next slide is talking about what are the components of the library. But imagine this scenario where you have some clients going for a backend server, and you have a middle box along the way that is blacklisting some flows. So this middle box will have a list of the flows that should go through and should not go through. So we call this list a set. So we call the list of the flows or objects a list, a set. And typically this is a large set, millions of flows or millions of objects. We call the way that you are querying this set membership test, which is I have an incoming flow. I'm querying whether I'm a member in this set or not. So this is checking whether this flow is one of the millions of the flows in this list or not. So what this library is providing this data structure, what we call a SetSummary. And the whole idea is, instead of storing this huge list, store this smaller data structure that can perform very similarly to storing the huge set. And I will come to how in a little bit. But that's the idea of the library, is creating this data structure that's called SetSummary that provides answers for membership tests. Anybody who is familiar with a plume filter will get this idea very quickly. So this basically is some kind of a plume filter. So the membership library, as I said, is a new library in DPDK 1711. And the idea here is it provides different modes or different types of set summaries based on the application needs. So each application writer can go and instantiate a new set summary based on his or her needs. Okay. So on the right-hand side of this slide is the modes of the membership library. There are 4 modes. Plume filter, as I was saying, is one of the modes, and vector plume filter. I'll come in a second to say what this is. And two modes that are based on hash tables. A hash table SetSummary and what we call a cuckoo distributor. The idea again is you have one or more sets. This can be one set or many, and each one of them have millions of entries, and you get an object that you want to test this membership along these sets. So you get X, and the question that you want to answer whether X is in one of these sets or not. The membership library will create the set summary and can get you back very quickly saying that X is not part of the sets, or it is very probable part of one set, and if there is many of them, which one it is part of. And pay attention to the very probable word that I said. So there is some false positive probability that says like 95% or 99% X is in set number 5. There is a very small chance that it says X is there, but X is not there. But when it says X is definitely not there, then it is definitely not there. Again, this is the basic idea of Bloom filters. Okay, so where can we use this library? There are hundreds and hundreds of usages for this library. I'm just listing a few of them here, but you can think about like classifications, network statistics, a lot of usages for the library. I listed 4 of them on the next slides as categories of usage examples. Let's skim through these usages. So the first one on the left is a distributed web cache. So in this example of using the library, we have a web cache sitting in the middle of the network that is caching objects on the backend web servers, and clients are coming in figuring out where to grab this object from. So these caches will cache the most used items, and the least used ones will be on the backend servers. So this client coming to a web cache, it wants to know where this item is. So if we're having a set summary along these web caches, these set summaries will very quickly tell the client where this object is located, whether it is one of the web caches or it is on one of the backend servers. Again, using the set summary will provide 2 things: faster lookup or faster answers for membership queries, and smaller storage. You can store a list of all the objects, but when you're storing a summary, you provide a smaller memory footprint or cache footprint, and also you can look up objects faster. The right-hand side example is using the set summary to solve a problem that is very well known in routing, which is detecting loops. So in that example, the set summary itself is stored in the packet header. And the idea here is that each node is checking whether it is member in that header or not. So as the packet is going around, each node is checking, have I seen this packet before or not? And I know that if my ID is in the set summary. So I go and check the summary to know whether my ID is there or not. If I see myself, this means I have a loop. This will be faster than waiting for TTL to time out. But also the same idea can be applied to any statistics. You can think of detecting heavy hitters or any kind of network statistics you can use set summaries in. Another example that I like is the Chrome that we are using today. So Chrome that we are using today in the safe browsing mode is using a set summary. Very similar functionality to a set summary. So what they have is a list of bad URLs, So like, for example, if it's porn or anything, I mean, you have a list of bad ones where you should not go to. And the SetSummary is summarizing what are these bad ones. So if I'm looking up xyz.com, I can look into the SetSummary and to see whether XYZ is a good one or not. If it is a good one, if it is a bad one, this SetSummary will come back and say, there is a very big probability that this is a bad one. So for that one, I will go to the backend server to do more analysis and more inspection. But if it is a good one, go ahead.
How does it know if there's a new bad one? How does it detect?
So the summary is...
Unless you're comparing to a list of what you are...
So you are storing a list of bad ones.
That's already known.
Yes, you are storing a list of bad ones. So this SetSummary will come and tell you with 100% accuracy, you are not part of it.
Understand.
So if you are a good one, you will go very fast. Okay. If there is some suspicious...
Has a complete list of all the good or bad ones?
This only stores the bad one. But you can think of them as millions of bad URLs. So you can store millions of bad URLs, but instead of storing a very huge list of bad ones, you are storing a summary that is smaller footprint and faster for lookup. Let's say instead of storing the full URL, I'm only storing 2 bits of the URL. So the full URL, for example, is 10 bits. I'm only storing 2. So I saved 80% of the storage. I also storing 2, so I am looking up only 2 instead of 10. So I also do faster lookup. So the idea here is that if you are not suspicious, you will go very fast. You are sure 100% that you are not part of the summary. But there is a false positive probability about like 3% that you are marked as bad, but you are good. So for this unfortunate case, you have to go into the backend server and will come back and say you are a good one, which is a very similar idea to all Plume filters, all summaries. But the library is just generalizing this idea. It provides a vector of Plume filter as one mode, and also provide a hash table-based summaries. So it is just a generalization of a Plume filter. Any more questions? Okay, so another example is collection tracker, where I have a SetSummary that is summarizing the assignment of the flows. So I have flow X is being processed or being handled in core Y. So the idea here is that when a new flow comes in, I want to be able to assign the flow to the least loaded core. And because this is a runtime problem, the least loaded core keeps changing. So the idea is I want to know whether a flow is new or not. So if I have a SetSummary that is summarizing all the flows that I have seen so far, a new flow will be marked very fast. So a new flow comes in, I know it is a new flow, I will send it in runtime to the least loaded core. Another example that I will have more details on is wildcard classification. And this is related to the OVS work that we have done. So let's jump to the OVS work and how we are, first, before jumping to the OVS work, the API for the library itself. So the API for the library, if you are familiar with the hash library in DPDK, it's very similar to the hash library. You have an API to create a summary, RT member create, and in this creation you have parameters for the number of keys, the length of the keys, and also the maximum false positive rate. So for the maximum false positive rate, if you say for example 5%, so you are sure that the summary that's created, the false positive rate will never be above 5%. It will be much lower, but it will never be above 5%. And then you have some insertion for elements. So you're adding a key in this summary. You have a bunch of lookup functions for the library. It depends on whether you are looking up a single element or a bulk of element. So RT member lookup is lookup for a single item in the set summary. RT member lookup bulk is lookup of a patch of keys in the summary. And then two other modes, which is lookup multi and lookup multi bulk, which is used when you have many destinations or many sets in your summary. So this will return not only whether the key is there or not, but will also return that the key is there and in which set of the sets you have. And then you also have an API to delete a member in the set summary.
So underneath, what is it using? It's using some sort of some list storage or something?
So it depends on the mode, but for example, a plume filter is an array of of bits, just vectors. If it is a hash table based one, it is an optimized hash table design that is storing only signatures. And if it is a cache one, I mean, there is a mode for also whether it is used as a cache versus no cache. So if there is a cache mode, you allow for overwriting the keys. These are the different modes of the library.
So this cache is not the CPU cache, right?
No, this is just the data structure used as a cache.
You're going to describe later the complexity in size and time in terms of memory, CPU, and time to compute all those?
No, I don't have a slide on that, but I will be happy to answer your question if you have any. Okay. Okay, so in this slide and the next slide, I'm trying to show to you a proof of concept of how good this library is. And to prove that, we used OVS as a proof of concept, and we changed the way OVS is doing flow lookup. I don't know how many of you are familiar with OVS, but for example, for the people who are not familiar, OVS is basically a switching, a virtual switch that has ports, and packets are coming in on these ports, and the job of OVS is to do a lookup on the packet to determine the action, like any switch, the action on this packet. So the way that OVS has structured their lookup mechanism are with 3 layers of lookups. The first layer is called exact match cache, where you are storing the full key of the flow and also the action with this flow. So a packet that's coming in, it will first be looked into exact match cache. If there is an exact match, it will perform the action. And this exact match cache will have around 8K. I mean, this is configurable, but it's around 8K, and for sure, as you increase the size, you increase also the footprint. But the default value is 8K. So if your number of flows is bigger than 8K, you will hit the megaflow cache. And the megaflow cache is a tuple space search for flow classification. So what they did is they have split the rules into tuples, where each tuple is matching on a given flow mask. And they did a very good job in inserting rules into this tuple so that the rules are inserted, and when you have a match, there is only one and only one match. So the basic idea of the megaflow search is, if you miss the exact match cache, you will go and search each tuple sequentially. You will go into the first tuple. If there is a miss, you go into the second until you have a match. And when you have a match, you have your rule with the action. So you can imagine that this sequential search of tuples, if this number of tuples is large, this sequential search of tuples will consume a lot of cycles. And this is one of the results for the case when we have 20 subtuples or 20 different masks. And typically mask is equivalent to different fields that you are looking into the packet. So 20 is not, I mean, we think is not a big number, but it really depends on the traffic profile of the network. But in any case, if for the case it has 20, 53% or 54% of the time is being spent just doing this sequential search until you get to image. The problem is clear, right? Okay. So that's how we changed OVS to use membership library. And by the way, there is already a patch being sent out on the OVS mailing list with this idea, and now it is under review and negotiations with the OVS guys on whether it will be part of OVS or not. But in any case, what we did is we used a SetSummary as what we call a first level of indirection. So since this SetSummary is very efficient in storing the flows, so you can think of it as a cache for the flows or an extension of the EMC. But it can store millions and millions of flows. So the packet header will come to this SetSummary, and the SetSummary will point to you that I have this flow, I have seen this flow before, and instead of going through the tuples, it will tell you, I have seen this flow before, and most probably, or 95% of the time, it is in this tuple. So you avoid searching the tuples, and you go directly to the destination tuple, or the tuple that you will match on. And this is the result that we have with OVS. So this result is comparing the original OVS DPDK with OVS DPDK, and we added the membership library. The number of flows, 10K flows, and the number of tuples are 20. And you can, I mean, our traffic pattern can hit any subtuple in a uniform way. And you can see consistent 2x to 3x improvement in using the membership library to speed up OVS. Again, this is just a POC that we use to evaluate how to use membership library, and when you use it, how much throughput gain you can get.
When you say it's statistical, if you declare that it should be found there,
Yes.
if it's not true,
If it's not true, it will go back to the to the original sequential search.
so it means that he doesn't have, he knows that it's there, but he doesn't know
Yes.
where.
Yes.
That's it.
Yes. So 3% of the time, you will go back to, you will have an overhead and go back to the sequential search instead of 100% of the time. And that's where the 2 to 3x comes from.
For 3% of the time, you need to pay the same penalty as before,
Yes.
plus one lookup.
Yes, exactly. But the one lookup is the membership library lookup, which is supposedly to be efficient than even one tuple lookup. Okay. Okay, so go ahead.
So, in OVS, you have indicated megaflow cache and also the microflow cache, different levels of them, right? So, I'm trying to
this stuff.
yeah,
Yes.
so which, so this blue filter is in which level? Because you have
So you can think about it is between this exact match and the megaflow cache. It is here. So if you miss the exact match cache, you go to the plume filter or the membership library that will point out to which megaflow cache. But you can also think of, you can replace the exact match cache with also this one. But I mean, this is debatable whether you want to do something like that or not.
But we could depend, only my question would be in that case, the uniqueness of the entire flow, because I don't know how much the Bloom filter can store. Because if you're you're storing few bits,
So-
and not the exact match.
Okay.
with so many
So first of all, for this mode, we haven't used the plume filter mode of the library. We use the hashtable mode. And the hashtable mode is storing a signature of 1 to 2 bytes. depending on also, yeah.
So the ML is combination.
So for a flow, what is the probability that you will have the same signature, the same 1 byte signature? It is very, very low. And this is the 3% that I'm talking about. So 3% of the time you will have signature collision. But 97% of the time you don't have a collision.
So the ML library has 2 modes. One is the Bloom.
Sorry, I can't hear that.
The ML library has got 2 modes. One is Bloom filter, another one.
It got 4 modes, yes. 2 categories, Bloom filter category and hash table based category. And for each one it has 2 sub modes. Okay.
What is the percentage of error vary with the size? How does it relate? Or is it more of a sample of the information?
You mean signature size? Or
Like, for example, the 97%
Yes.
you mentioned. Is it linked to somehow a function of the size of the number of flow that you need to sample?
no, it is only a function of the, if you are using a hash table, it's only a function of the signature size. So if you are using 1 byte signature versus a 2 byte signature versus a 3 byte signature.
Okay, that's
But it's not a function of how many flows there are, whether it is million flows or 1K flows. Okay, go ahead.
Repeat that part again. I didn't follow.
So the false positive probability, which is the probability of accuracy for a set summary, only depends on the size of the signature that you are storing. Does not depend on the size of the number of flows.
So then, what's the rationale for having an 8K bound on the?
No, the 8K is for the exact mesh cache. This is a bound that OVS has done because you can. Their key is very long. It's 52 byte keys, so you cannot store millions of keys there. But for our case, we have a summary that is taking these long keys and storing only a summary of it.
Right, and your
So you can have millions there.
your summary is 2 bits.
The summary is 2 bytes per key, not 2 bits. 2 bytes per key, and you have in one packet you have 16 keys.
So to
But again, these are all configurable. You can change the configuration in the library.
right, so yeah, to write at 2 bytes, you must have used some sample size target. So what was that sample size?
So the false positive, when you create the summary, you give it the false positive probability, your absolute maximum false positive probability that's acceptable in your case. So the size of the signature is calculated out of, as a library user, you just say I can tolerate 5% false positive probability, and the library itself will go and determine what are the sizes and everything. So this is not configurable. You can only configure the false positive, and the library will go and compute what is the size of the signature and how many keys per packet and everything. Does this answer your question?
Yes.
Okay, so I don't know whether I took more than my time or not, but only my last slide is about future work. So we are looking into applying this library into more workloads. And if you guys have any workload that you think can use this library, I will be happy to talk with you. You can also send me an email. But also we are working on an ACL implementation that is using this library to instead of using tuple space search, so we can have an ACL library with high update rate. These are the 2 future work for this library. And that's it for me. Legal, which is always good. And then this is my email if you want to send me any questions. Go ahead.
So there's a live RTE ACL also, right?
Yes, that's true.
How is that different from this?
So the RTE ACL is a tree-based library. The update rate, so we're not saying that we are replacing the RTE ACL, but this might be another mode that is using tuple space search for ACL. So as a user, you will have 2 options: a tree-based mode that is very fast in lookup, but the update is not that good, and the tuple space search that is in between. Maybe a good lookup, but the update rate is much better than the tree-based solution or trie-based solution. But anyway, I am not commenting on future releases of an ACL library. This is only our research work. It might be there or might not be there in DPDK.
So you're saying that yours is not as fast as the tree-based. Is that because of the false positive and having to go to the back end?
You mean fast for lookup or fast for lookup? I mean, we haven't finished the implementation yet, so we don't have results yet. But if you think about it, tuplet-based search, traditionally is slower than tree-based solutions. But it might not be the case for our implementation. But we haven't finished the implementation yet. But this is part of our future work. Any more questions? Go ahead.
Do you have performance numbers that you can share
For
example, the hash?
the membership library, I already shared the POC results for OVS. And in the OVS mailing list, we also have many other traffic patterns, and we shared the results there. Are you looking for a specific application in mind?
Yeah, I'll talk to you after.
Okay, I'm done here.
Thank you, Samir.
Thank you.
Anybody who has the Wi-Fi information? Yeah, so now we have Anurag on accelerating virtual machine access with the SPDK.
I just did the presentation, but I don't know why it disappeared.
Oh.
Just taking time. Yeah,
Okay.
well, it's going in. Oh, perfect. Okay.
Go ahead.
Just gonna move this. Ready? Okay. Hi, everyone. Good afternoon. My name is Anurag. I'm software product manager at Intel for storage software. And I work in the data center group. I have a confession to make before I start. I had too much coffee on the way here, so I may be going very fast. If I go fast, feel free to interrupt me and ask me to slow down. Okay, so how many of you have heard of SPDK? Storage Performance Development Kit. Awesome. Almost everyone knows. Good. Okay, so how do I? Okay, it's just slow. So I will quickly go over why SPDK for those of you who are not familiar with it. So SPDK is basically a storage acceleration software. What that means is this bar explains it. So on the left-hand side, you have the hard disk drives, which are way slower, which is what a lot of our software are designed to, to that needs. So you see the blue is the drive latency, the orange is the controller latency. When I say controller, I don't mean the controller in the NVMe drives. What this means is like your HBA, the SAS SATA controller. And then you have the green, which is the software latency. You see on the left-hand side for hard disk drive, software latency is pretty much about the same as the others, but because the drive latency is so much, software latency doesn't matter at all. When the data comes back in milliseconds, you optimizing your software latency, which is in microseconds, won't matter. As you move towards faster drives, like go towards NVMe drives, I don't have the 3D NAND here. That should come somewhere in between SSD NAND and your, the Optane. But as you move towards the 3D NAND or the Optane, you see the drive latency dramatically decreases, and your software latency here is closer to 30-40% is what we are showing, and this is the most optimistic view. If you take the full software stack, it may go beyond 40%. What this means is you're spending so much money on the drives, paying so much to get the full performance, but software latency is eating up some of it, like 40%, which is quite significant. So as you move towards faster drives, and in future more faster drives, software latency is something everyone needs to address, otherwise it's eating up all the performance. And that's where SPDK will help. Sorry, it's just slow. There you go. So what is SPDK? SPDK is based off of DPDK. If you're very familiar with DPDK, it kind of follows the same similar analogy. So it uses user space, lockless, poll mode components. So lot of software in storage takes tons of time in doing the context switches, handling locks and interrupts. The data, especially in the Optane 3D NAND timeframe, it comes back in about 10 to 11 microseconds, but your software takes over 30 microseconds to do all this handling. So doing it in user space, lockless, and poll mode will give you back those 20, 30 microseconds that is being wasted in software. And because of which you can actually get up to millions of IOPS. And SPDK is mainly designed to extract maximum performance from these fast NVMe drives. You do have optimization in the kernel, but it is not catered towards only NVMe, whereas with SPDK, it is the only sole purpose of its creation is to help with speeding up your drives. The good news is it's open source, and it's similar to DPDK's BSD license, which is the most free license there is. And if you want more information on SPDK, spdk.io webpage should be able to provide that. I do have some more on the community in the next slide, but that's the place to go to get more information on SPDK, to get the code, etc. So there are links to our GitHub from this webpage. And also we have SPDK project Twitter handle, so we are hosting events. This year, a lot of events on SPDK, similar to DPDK meetup. We are hosting an SPDK meetup in May. So all the events information will be tweeted in SPDK project handle. Yes.
I didn't see anything about the hybrid SSD hard disk hybrids. You didn't need to show it. Just wanted to compare.
Oh, you mean like in the graph there?
Yeah, if you go back to the graph.
Oh, sure. So this is just an example. There are a lot of things that comes in between. We just didn't fit in everything. So the question was, I didn't address hybrid drives in here, but as I said, this is just an example to show, that the speed increases when you move towards this way, and SPDK helps. Exactly.
The question is, DPDK also does the poll mode, drive and memory management, a lot of things are common.
Correct.
So libraries are common. So what is the difference then? So I guess most of the elements of the libraries are
right.
common.
I have an architecture diagram that will show you what are the different components of SPDK and how is it different from DPDK. And we do use a lot of DPDK APIs, so we don't reinvent the wheel. So this is just to give you a quick picture of the benefits of SPDK. I am going deep dive into the actual, how the SPDK helps, etc. But just to show you, to get you more interested in listening to my presentation, basically. So with SPDK, I do have some graphs later to show you this performance. So basically, you get over 10x more IOPS per core with NVMe over Fabric. So you can use SPDK to access local drives or drives over the Fabric, and you do get a lot more benefit with either cases. And just with using local drives, and these are all comparison to Linux kernel. So this is using user space versus using Linux kernel is what we are showing here. You do get 8x more IOPS per core. Again, these are all not 10%, 20%. It is significant performance gain is what you see. And we did integrate RocksDB with SPDK. And if you ask me why RocksDB, why not any other database, it was just something that we chose because it was more common key value store database. So with that, we did see that you get about 50% better tail latency. And we do have SPDK, you can use it with virtualized systems. So that's something we added later last year. And with that, you see over 3x better performance. And we did have some tests, and I have some of those performance numbers later in this deck, where we tried with Optane SSD, and then the last one is where engineer gone crazy. We thought, okay, let's add the maximum number of Optane SSDs to a system and see how much maximum performance you can get. And you can see about 10.8, about 10.8 million IOPS. And the reason it stops there is not because SPDK saturates, it's mostly because the PCI lanes, you are bound by how many PCI lanes are available. Yes.
It all depends on, this is a general numbers, right? It all depends on read-write ratio.
Yes, I do have some
numbers. We'll cover all of that more.
You're right. Sorry, good question.
So this also runs in user space, operates like
DPDK.
DPDK. In the DPDK case, it's next DPDK is sort of biased towards non-terminated lines, for example. In this case, this would be storage, and you're accessing the storage from user space. For that to be consumable, you have to throw it back down to kernel, or what's the scenario for everything?
I have the exact flow that you're asking. It's coming up next. Yes, we'll address, and if you have any more questions, then I can help answer. Okay, going forward. So this is just a quick glance at the SPDK community. We are a happy family. So basically, you have the spdk.io webpage to get more information. We do have a mailing list there if you have questions. We have, instead of emailing one of us, it's best to go there and email your question because we have community using SPDK and they may be seeing similar issue and you'll get very fast answer. We do have a IRC channel, so please use that. You get very quick response there. And we have Trello if you have any new features or you have any questions regarding the features or new ideas. This is the best tool to use. And since about a month, we started our weekly calls. It's a community call, so basically it's a good place to go listen to other community members, what they are doing. If you have any questions, it's a good place to actually catch some of SPDK developers and ask your questions. This is mostly on Thursdays, and the Twitter, I do post the caller ID and then the conference number and the password, etc. So you can just go to Twitter and get those information and log into the call. But spdk.io webpage also has a blog post that they post the agenda if you want to follow that. So this is our community and there are a lot of resources available. So I just want to answer your question, actually one of your questions about difference between DPDK and SPDK. I want to quickly flash the architecture diagram here. Any questions? I thought someone was raising hand. You have a question? Okay. So this just shows different, let me just go through this and then yes, I'll take a question. So it has three parts. The bottom one is where you get the user space drivers. So we have the user space NVMe general PCIe driver to access the local drives. There is also a user space NVMe over Fabric driver, and we also have provided user space DMA driver, which is a Intel Quick Data Technology driver, which is off the chipset. So these are all user space drivers, and this is what we offer through SPDK in order to access the storage. And on the top are different protocols that we support. So we support SCSI target, we also support NVMe over Fabric, and Vhost. Vhost is the virtualized system. So you can actually have virtualized system and use SPDK to access drives, either remote or local. And you can, and the middle part is where we implement the block abstraction device. What this means is you may be accessing any of those protocols, and you may have different drives connected. Application need not know about it, and the abstraction layer will abstract it and be able to, you can access Ceph or drives, or you can access the AIO drives, or you can even access NVMe over Fabric off the way to another, over the network to a set of JBOF or drives over there. So that's what the block abstraction device provides. And there is a QoS feature. If you're interested, I can give a little more information on that. Basically, on the virtualized system, what that helps is the QoS is where it prevents one VM from hogging the system or taking all the IOPS from the drive. So basically, there is an option to go set up how much IOPS you want to allow each VM, and that is something that we have added. There is a block file system and block store. So the file system is not complete file system. It's more a smaller file system, basically used to integrate RocksDB is what that is. And QEMU is where we have integrated SPDK into KVM. So if you are using KVM, then you don't need to make application changes. You should be able to get the benefit of SPDK because we've already integrated into the KVM hypervisor. And that's what we'll be focusing on next is on the Vhost SCSI, Vhost block, and QEMU. Any questions? Okay. So we're going to go deep into the virtualized system with SPDK. I just want to give a quick, you're all familiar with VirtIO. Basically is a protocol to assign an emulated device to a virtual machine. And SPDK uses this. So basically you have multiple VirtIO device types available. What SPDK basically uses for this is a VirtIO SCSI and VirtIO block. Just wanted to flash that. Okay, so now we're going to see the flow without SPDK in picture. So our guest VM wants to send an IO request to the device. It allocates it in the virtual queue. So what happens next is an exit from the VM, and the request goes to the QEMU for processing. And then that request is issued to the kernel. Now the kernel will pin the memory, and it allocates that request to the device. The overhead here right now is with the guest having to exit into the host, and then you have to do the context switch into kernel, and then you go send the request off to the device. And then the device executes the IO, the data comes back to the kernel, data goes to the QEMU, and then the VM entry happens, and then the data is written back to the virtual queue, and then a notification goes to the guest saying that the interrupt completed, your data is here, go fetch it, and the guest takes it. So there are a lot of software overhead in the flow before, and that is we're going to see. So the vhost, which is the SPDK, the vhost target, which is SPDK component, can be integrated in the kernel or in the user space. I want to walk through integrating it in the kernel and show you what the benefit you will get with that, and then we'll show you the next one would be in the user space and see what happens. So the vhost target is not part of the hypervisor. It's separate from the hypervisor. And then there is a communication between the two, and that's initial communication. After that, the hypervisor is out of the picture. So the initial communication is basically to give information about the VM, like where the memory is, how many virtual queues is allocated, and the location of the virtual queues, etc., is what is communicated. And it uses vhost protocol to communicate between the two. Once that is done, the hypervisor would be out of the picture. So that's what you're eliminating in this flow, the hypervisor overhead. So the data the request gets allocated in the virtual queue similar to before. Now you see that the request is not going to QEMU because we removed the hypervisor part from that flow. So you save some there. But it still goes to your kernel, so it gets the kernel, and it has to be done through the virtual doorbell, and the kernel is woken up, the request is sent to it, and it pins the memory, does the same thing as before, sends the request to the device, data comes back, and then it has to send information to the guest saying your interrupt completed, go fetch the data, and the guest gets the data. Here we eliminated the hypervisor, but there is still overhead associated with kernel, so the exit is not completely removed. Now is the SPDK. This is basically doing the vhost in the user space. So there are multiple things here. We do the same thing, the initial configuration between the QEMU and the SPDK vhost. That way we eliminate the hypervisor from the picture. So SPDK actually sets up a Unix domain socket in order to do the control transfer, and then you have the vhost protocol that it does similar to before to transfer the configuration information like where the memory is, etc. And then it allocates, like each VM can allocate one or more virtual queues in order to send the information, basically the IO request. So let's look at the flow now. So the application allocates IO request in the virtual queue as before. Now there is no kernel involvement. What's happening is SPDK is actually polling. And polling works better. Like you may ask, oh, you're allocating one CPU for polling. Does that mean the performance is going away? In fact, have performance data with this, where it shows that because the data from the drives come back in lower microseconds, polling is not bad because you're not polling for a long time. And you can use algorithms there to see, like, I want to poll only a few microseconds and I want to go sleep or whatever, or do other things. So because SPDK polls, as soon as the request is in the virtual queue, it's able to get it and then send it to your device, and then the data comes back. The only thing here you see is on the way back, I think that's a question you were asking, it still needs to go through the kernel because the VM doesn't poll. It's only the polling done in SPDK, not the VM. So the data still needs to go back through kernel, and the kernel still needs to do a doorbell and interrupt the guest to say your data is there, and then the guest gets the data. Oops, sorry. Any question on this before I proceed? Okay. So as you saw, the path, yeah.
Sorry.
Sure.
So SPDK in the host, the Vhost, is polling for every single guest VM?
Yes.
Or
Yes.
does it have a per
You can
VM?
set up processes to, or a threads to do that.
Okay, so there are 64 VMs and the 64 threads polling?
Yes, and I think it can be shared too. You can have a thread, like it's not like each thread is polling its own VM. You can have a thread poll this and then the next VM and then the next VM, like a round robin. I mean, it all depends, yeah. That's how it would be doing. Not you won't be assigning 64 threads to poll 64 VMs, which won't be optimal.
How many transactions per second are you polling for?
I don't have that information, unfortunately, but I can get back to you on that. I think I have the performance data though. I mean, hopefully that should give you some information there. If not, I can get back to you on that. So here, on the data back, it's going through the kernel, and if you want to eliminate that, then we have the option of virtIO SCSI and virtIO block is for legacy, where you can integrate that into your application, where your application is polling. And it eliminates that kernel path where you have to interrupt the guest. Now the guest can be polling too, that way you save the time. And before I wrap up, I just want to go through, just highlight the logical volumes feature that we recently introduced in SPDK. So in the virtualized system, typically you don't have where each VM is accessing its own SSD. Usually makes sense, like usually they do sharing. So you may ask me, okay, I can use SRIOV, why do I need logical volumes from SPDK? SRIOV, first off, is not available on all the SSDs that are out there right now. Secondly, you can't do snapshots with SRIOV. Snapshot is basically where you take a snapshot of your, save your VM's data, and where you can copy it to, if you're creating another VM, then you can copy it to that instead of redoing it all. And that feature is not there in SRIOV. So the other thing is LVM. LVM provides similar thing in kernel. But the problem with LVM is it's again kernel Linux block, which means you're going through the kernel, which means you're not doing it in user space. So SPDK provides a feature called logical volumes, wherein you can actually take an SSD and divide it into different blocks and assign it to VMs on the fly. This can be done at runtime. And this is something that came out in October last year, and that's available through SPDK. Unfortunately, I don't have time to go through the whole flow there, but that's for another time. Any questions on this? Okay, now for the fun part, we're going to look at some performance with SPDK. So this one is it's a bit confusing. I was supposed to eliminate the middle one, but I will go through this in detail what exactly this is. So this is with QDepth 1. The Linux part is where it's the first example I showed, where everything is going through your hypervisor and the kernel. And the middle one is with QEMU eliminated. I don't know why we are showing it still with QEMU, that's why I said it's a little bit confusing. I should correct this. And the last part is the user space vhost. So the first one is no vhost, second one is kernel integrated vhost, and last one is user space vhost. As you can see, you do see a very good, like it's with SPDK, you do see over 3x performance benefit using the vhost in the user space.
But you save efficiency. What are the efficiency aspects?
CPU. So you can actually scale up to, I do have that in the next slide. You can scale up to 96 virtual machines with SPDK, whereas with kernel you saturate with 48 virtual machines. Your CPU is executing at its full capacity. You can't do anything else. Whereas with SPDK you can still run some storage functions like compression, encryption, etc.
So the one that says SPDK, so that's consuming it in user space.
Yeah.
So does that mean that you have to have some kind of a user space file system and storage stack in the user space to be able to actually make use of this? Or is
No.
it constrained to certain scenarios because of that?
So the user space is only through for the I/O path. You are still using your Linux file system, but only when you're accessing the I/O is where it goes through the SPDK functions.
But the device performs a DNA into a user space queue.
Correct.
So how do you map that back to kernel space from consuming VM? I'm not understanding how an application will consume the data that's DMA to user space for this.
Right. Let's talk offline. I can go over that. Sorry. Okay. So in this, where we are showing, this is the one where we thought, okay, let's see how much performance you can get adding all 24 octane drives to the system. So with this, actually, you could scale. You can get up to 9 million IOPS, but the CPU efficiency is where basically you can scale more VMs in this. Like as I said, up to 96 virtual machines, and if you see the kernel is saturated with just 3.4, that means your cores are done. Whereas here, cores can still do a lot more things. I had one more picture where it showed. CPU, sorry, what?
CPU
Utilization, how much percentage? I don't know if I have it in this deck. But maybe I can send it to you. Does it show CPU utilization? Actually, it does here. It does show here. So, yeah. So SPDK, with SPDK, your CPUs can do a lot more while giving you more I/O performance. So just want to show you some of the use cases that we would use SPDK. So this is where you have multiple virtual machines. Each one has its own logical volume, device abstraction layer, and then you use the user space NVMe driver to access NVMe disk. It can be remote or local, although we are only showing local here. This one is for NVMe accessing drives over network, NVMe over fabric, using SPDK and NVMe over fabric user space driver. And here you can actually use, we have integrated into Ceph too, so you can actually use to access Ceph cluster. So that's all I have for today. Yeah.
Again, I was coming back to application specific, for example, streaming applications versus simple read-write applications, and then just store it and put it in the hard drive.
Yeah.
These things vary, right?
Depends on what kind of drives you're using. I've had questions where people ask, oh, does SPDK work with hard disk drives? Yes, it does, but if your hard disk drive is taking milliseconds to get the data back and you optimize microseconds, you don't see it. I mean, it works, but you don't see anything. It'll be same as your Linux kernel because software is not the problem.
Any persistent memory have you looked at?
Yes, we do.
So when people ask me persistent memory question with SPDK, first thing I want to tell them is it's different. It's very different because SPDK is I/O optimization. Your persistent memory is memory. However, if for some reason applications still want to do block access to persistent memory, then yes, SPDK. I think I have that in the architecture diagram here. Let me go back quickly to the, if I can.
Do you have your own Intel's persistent memory implementation?
So,
IBM and so.
So you see the PMDK block there? So basically you can use that to access persistent memory through SPDK from user space. What that means is there is something called storage access through persistent memory. That means your application don't have to change their, you don't have to change in order for persistent memory support. You can still do block access. And if you want to do that for some, if you have already implemented SPDK and you want to do that from user space, then you can use this to access.
Yeah. There are a lot of new nanotechnology-based memory devices, not in large application, large market, but still they're trying to claim the space between your DRAM and the SSDs, whatever fastest SSD that you show. Are you looking at those things of how SPDK can do anything better?
So SPDK should be able to help for any fast media.
Have you implemented, tried?
We have tried with mostly NVMe drives because it makes sense because we can show performance with NVMe drives. If you do anything slower than that, we can show that SPDK will eliminate, as I said, it's in microseconds, so you may not see it.
There are a few of them.
You may not see it, yeah.
MRAMs and so on.
But it won't make it any slower. So if you have a hybrid kind of storage system where you have some SAS drives and you have some NVMe drives in system and you want to use SPDK, SPDK will accelerate your fastest, your hot, access, like basically your fastest drives.
Is it latency intensive reduction? That is where your focus is for the.
That's where you can see the help. Okay. It helps other places too, but you won't see it. But if you're running with, as I said, in a hybrid system where you have some SAS or hard disk drives, those won't perform any worse than it is already. It will be same performance, but your fastest one will be more faster. So what this does is it eliminates software latency, which is in microseconds. So if your latency is already in milliseconds, and if I take out 30 microseconds, you won't see it, but it's still faster. It's faster by 30 microseconds, but you won't see it. Yeah.
You said at VM level, is there any support for mirroring at VM level?
There is actually. We do have, I don't have it here, but there are some new features coming along that line. Yeah. Like snapshots is one, which I don't think I have it listed here, but yes, with logical volumes, that feature, I think it came in January in Q1 release. And then we are also doing something called I/O provisioning, wherein you don't allocate all the SSD space for the VM, and you allocate it based on its need, and that's along the line of snapshots, and that is also coming in, I think, in Q2.
Suppose if you are mirroring at physical level, at VM level, it may affect performance.
Yeah, but if we add it in user space, it will definitely be better than going and doing all the other overhead. And we are adding those features into SPDK. It's coming slowly.
Yeah, just wondering whether do you have container support?
Good question. Not yet, but we are considering it. And because this is an open source similar to DPDK, we do encourage all of you to, if container is important, we would encourage you to contribute. So.
I'm a conference advisor to what's called Flash Memory Summit. which 6,000 people attend.
Oh, I attend. We had a demo last year.
If you could come and present some of
Oh
it.
yeah, sure. We did last time.
You will get exposure to 6,000.
No, I will be happy to. And I think we are submitting some papers to Flash Memory Summit this
I know,
year. But yeah,
But if this part, oh yeah, someone is doing this?
yes, yeah, there will be. And we'll have a demo too. Last year we had fire, so we couldn't actually show SPDK, but this year we are planning to.
Hopefully
Yeah,
you will.
hopefully, yeah. So, yep.
So is there some sort of optimization in that polling thread in Vhost?
Um,
Because I'm thinking about, say, there's a user application doing I/O in a loop, right?
Right.
Horrible code, but let's assume. How would that, so the Vhost polling thread is now polling every few milliseconds or something. How is it going to be optimized?
We typically do round robin, depends on if it's in virtualized, as I mentioned, if it's in VM, we do round robin, but that's a good question. I can connect you with my principal engineer who should be able to answer those questions in more detail than I possibly can. So, oh, you're from Intel. So yeah, Jim Harris would be the person to talk to.
Good job.
Thank you.
We're actually running ahead of time. Yeah, actually we can take a break. Are you from Intel? Okay. I'll give you my card and please shoot me a question in the hand. Connect you with the right person to answer the question, because that is more technical. So, we have the next presentation. No, actually, Samir finished early and then you finished early. So the next we are actually running out of time. So our next presentation is at 4:35. So we're actually short of time.
Coffee?
Yes.
Is coffee there?
Huh?
Is there coffee?
You know what? You can all be our guests and I can give you.
No.
No, it's on the house, so, but you have to be with someone else.
Yeah,
No.
we can escort you to the
You can
campus.
escort me to the campus.
So we have 10 minutes?
Yeah, we have,
4:30
15
will,
minutes, yeah.
4:30 will be back.
4:30, yeah. So, those who want to get coffee, either come with Ranjit or myself, or Anup for that matter. Coffee?
You take them, I'll take them.
Yeah. Same presentation. Coffee, last call? Coffee?
Oh, when you going to work, I will call you.
Yeah.
I want to be the only person. I feel impressed.
You mean like SSG? You should be able to, yeah. The thing is, we don't have to, but this is not.
Yeah, I was curious about the performance of the
No, you have to,
hash
not, so double that is all of this is available in suite.
because I don't know enough about the internals of it.
This is integrated with hypervisor, so yeah, you
Gel in
just.
my mind, I don't really know what you're talking about, but I don't know how it's working.
I'll give you my card, and if you have any questions, you can shoot me an email.
Okay.
We have also the Rebel guys have a lot of.
Set, especially, we are looking to integrate SPDK and some of it is integrated. It's not integration as a
If you have any questions about, if you need to know the details about how the library is implemented,
Yeah,
I can
application,
help you.
SPDK is not
I
like,
mean, is
it needs
it all
changes.
public?
You're
Yeah,
using
everything is public. The slides are public, the library is public, it's public.
Then your application will benefit those, where
I'm just trying to find performance.
you have on the way to the drive. So those things can be done without.
There is RT hash,
But if
which is based on Coco hash.
if your application, for instance, is doing Intel, then using SPDK
There is extended table in DPDK, another hash
Just
table.
like DPDK, it's it's library.
There is membership library.
There are some changes.
Well, depends on that, on your application. If you can show me your application in high level, like I can point you
Yeah,
to
I
which
mean,
library.
SPDK, any Linux, you should be able to.
Okay,
Yeah.
I mean, in
I
short,
think we also have some of
What about
the
ideas like that, my team.
So, I don't know if you attended Oracle World. Last year, they did announce that they're integrating it in their database. So, Oracle should be.
I'll be more than happy to discuss that with you because we already have done some testing on that as well.
And we have integrated in Rocksteady, but we are open to working with other databases. So, it's a matter of, if it's proprietary,
Which company are you?
right? So, they have to.
Okay.
But we work with ecosystem.
Stuff for
The partners.
No, I mean, we are in the lab, so we are not the part of the. Yeah.
Yeah. So.
But memcached is one of the top features for all of these kinds of things. We have done extensive
higher level.
testing on which one
It's
to
much
use.
at a higher level, and the whole way it's designed is.
But you can first go
But
on
we are testing, so we
web
know
site
that
for
all the
DPDK.
performance data
The
that we
RG
show,
hash
say for example,
your first
Samsung or.
choice if you want to have exact
Only
match
just to click. But yeah,
for keys. And if we don't, then what I presented today is will significantly boost your performance. Okay. But I mean, I will also get to answer any of your questions if you have any after looking into these things.
Okay.
Okay?
Yeah.
Okay. Nice to meet you.
Thank you.
Can I be a part two?
Yeah, sure. Just a few letters. Thank you.
I mean, if you're not using an Intel hardware, you still, and obviously it's not so much for some of the, it's mostly on Intel too. Use probably in the future, or if you use it on non-Intel hardware, will it still work or is
It will still work, but
you don't know the performance?
I don't know the performance.
So you would know your intuition maybe that should be faster, I mean, the whole strategy is not going to change. It should be faster, you know how much more faster.
Yes, exactly. But as we are developing this library, we make use of some of the intel features. But if I mean, like for example, AVX, AVX is the vector instructions in that. So we use AVX to compare signatures. This will speed things up. But if AVX is not available, then we go into like search. Compare one by one, which still will be fast, but you are not taking advantage of these features. But we don't have the numbers that will reflect that. Sure.
Which one? No, what is that? I know, but it says, I signed up, but it says, you know, they're looking for a co-organizer or something. Is that the one you're talking about?
Yes, yes, we have.
Are the member partners?
So
Where is that? Oh, you know ZGC, yeah?
It's part of.
I don't pronounce it as good as ZGC.
Yes, I think so.
Z, I pronounce Z hard. ZGC. That's all. And I signed up, I don't know. This is going to go on to the other sequel already. Yeah, something like that. There's more to it. Just the numbers of event session. Yes.
Oh, we will post in one of them.
Yeah.
We will post a link on the media. Michelle will post that.
See, if you did.
So usually
I did my own hand one this morning.
and I don't know.
Luckily,
Because I shared, I think.
I missed that because yes, it was the whole day, starting from 8 o'clock. Because when I moved away to Arden area, Blossom Hill, Cardi area. Coming in the morning is can be about 6:30. Otherwise, I don't get. That's one. People events, I don't know which one.
Sorry,
I like to go to CGC because those events are so good. You go to, you know where CGC is? It's part of the 100. There are so many events. I did my own nano event. We did a nano event of microfluidics. Are you into nano? I'm not seeing you in nano event. Yes. That's also separate. But I organized nano microfluidics.
I find out from 1:30 to 3:30 and then from here.
No, we all go to a lot of events. There's another one in. Probably sign up.
Those slides are not on the shares right now. They will be.
It's kind of broad.
However, the video is already full because we are streaming live and as well as getting recorded. So the videos are already not slides. And I don't work for YouTube either.
We check.
You know, you have conference.
We can check. We're not speaking at the same time. So,
Huh?
You know,
I don't know.
organizing any day, nano. That works.
So you give them a signal if
Well, there's also a, in Italy, and there's also a Italy.
So we start at 4:35 or?
Yeah, 4:35 is what we have on the schedule.
Okay.
Actually, we had 4:40 on the schedule.
My schedule is at 4:35.
Okay, I don't know. It's on the sheet. Michelle must give me an older slide, man. I don't know.
The one which is on the YouTube has 4:40.
Maybe.
Or we just start.
Did you mean screen or stream?
Screen. Yeah.
Wow. You guys are high technologists.
Okay.
Okay. So I guess we'll start now. Making networking apps stream on Windows with DPDK. Yay. So this was actually announced at the DPDK summit, right?
Yes.
In November.
Yes.
But this was the first time that this was announced. So this is a big deal, actually. So we have Omar Cordana from Microsoft. He came all the way from Seattle. And we have Ranjit Menon from Intel. So Omar Cordana is software engineering lead at Microsoft. He drives the design and architecture of Windows Virtual Networking, SDN, and acceleration. Ranjit Menon is a network software engineer at Intel Corporation who has dabbled in various networking technologies for the past 10 years. I'll give the floor to Ranjit and Omar.
Thank you. Okay, so we stand between you guys and dinner. So we'll try to make this entertaining and fast. Okay. So again, this is a subject that was presented at the last DPDK Summit North America in November 2017. It's basically a refresh of what we have. Disclaimer notice. So why would we bring DPDK to Windows? How are we bringing DPDK to Windows? How does this compare with the other technologies we have inside of Windows already? So we already got kernel mode networking, we have some user space optimizations, we have all kinds of accelerations. So where does this fit in? Okay? Lastly, what's our roadmap? Where do we want to take this? What do we want to do with it? We'll cover all of these things in this presentation. Now, latency matters, throughput matters. Okay? Many ways to get there. We have many scenarios, and we hear from a lot of our customers that they're asking for faster networking. No matter how much acceleration we give them in terms of hardware, new scenarios always arise. So a lot of our cloud properties, both inside of the public cloud and in the private cloud space, which we address through software-defined data center solutions or a product called Azure Stack, these require very high packet processing. Okay? Those technologies today are not sitting on something like DPDK. We need to make them bigger, better, faster, and much more efficient, so we need to use something like DPDK for them. In the finance space, latency obviously matters. We don't need to dig into too many details for that. In the media production space, latency and throughput and packet processing become very, very important, especially as they move up to very high definition video, 4K video. All of these things become more important. Network security, deep packet inspection. If I'm doing deep packet inspection, I want to do it on an NFV appliance. Well, I kind of need something that's very efficient to do that. Kernel-mediated I/O is never going to cut it for that. Okay? And obviously, NFV appliances. The use case for DPDK and NFVs is super clear. Lastly, we're looking at IoT gateways and aggregators. So you have your factory floor, you've got all these sensors everywhere. You want to have some kind of communication between that and the cloud. You don't want to send everything back and forth. You need to have some kind of an aggregation point locally on site. You don't want to pay all the money to the telcos, and you don't want to be hit with all the latency going over a WAN. So you need some kind of a very fast local processing to capture all this data, okay? And lastly, my favorite, it's obvious where this is going. At some point, applications are going to bring along their own stack. very finely tuned stack, specifically set for their exact needs. And we don't have to go too far into the future for that. If you look today, Chrome uses Quick. It's basically a UDP tunnel, and they have their own stack reliability, retransmissions. They have all the logic inside of their browser, inside of user space. There are many other scenarios like that exist where applications are bringing along their own finely tuned stack just for their needs, and this allows us to provide a platform for them to build on that works both for Linux and for Windows. Okay, so this is the journey. Yes?
Do you use DPDK just for I/O, or you also use other libraries in DPDK?
Well, right now we're just getting the platform stood up on Windows, and that's what we're covering here.
Yeah, but just for the I/O part.
Presently, it's right now only
Yes.
IO networking.
Yes. So the journey for how we got to this point of getting to DPDK. So remember in the 2000s, right? It was just dumb NICs. Network speeds were not enough to saturate CPUs. Now you start fast forwarding, CPU speeds start to scale up. Network speed starts to scale up, CPU speeds start to sort of stay idle, and now you've got the classical problem of the network overrunning the CPUs, so you have to go to accelerations. So typical stateless accelerations, we all know what these are, but then eventually you get into the stateful offload accelerations like RDMA, iSCSI, et cetera, et cetera, et cetera. Now, with those things, you can do some optimizations. For example, we have a technology called Rio sockets that basically does memory mapping of the underlying NIC buffers to not exactly user space, it sits in kernel space, but it gives you, it reduces the number of copies that you have to do through your networking stack and gets you better performance, okay? Then eventually you get into the virtualized infrastructure environments, and obviously that's all software-based and you're incurring some very significant overheads, so then you bring accelerations back into that, and you get into very interesting cases with SRIOV, and you can start giving out virtual functions, and at least for Microsoft specifically, we're very interested in the multi-tenant space specifically, meaning we have to be hostile multi-tenant safe and secure, and we have to be able to control what a guest places on the wire and how much he places on the wire. So in the SRIOV space, even though that technology exists today and is used for the multi-tenancy space, it's not exactly applicable until you can secure it through both QoS and controlling what gets placed on that fabric. And then finally, we get to the point where we have DPDK on Windows. So now we've enabled kernel space applications to go very fast, user space applications through kernel mediated I/O, guests through virtual functions, and now we cover the user space aspects, okay? And with that, I will hand this over to Ranjit.
Thank you. I'll just hold this. So thank you, Omar. So like Omar mentioned, we kick-started this project sometime last year. There was talk about this going on, years before that, but there was some disconnect in the way Microsoft and Intel were approaching it. And then finally last year, I think almost a year ago, around March of last year, we said, okay, let's meet, let's try to get DPDK, the native solution on Windows first, before we solve anything within VMs and virtualization and all that. And so we came up with these certain goals that we wanted to meet. The first one, like I said, was to bring native support of DPDK to Windows, and so that it would natively work on Windows, not in a Linux VM or something like that. The second thing was we wanted full parity with Linux, so that you have performance exactly that you see on Linux would be the same. You could replicate the same thing on Windows. There was no point if you could do the same thing on Windows and Windows was 2x slower than Linux. There would be not much of an adoption in the industry if we did that. The third thing was we also had to make sure that other IHVs could easily port their PMDs or whatever to Windows, so that this is not exclusive an Intel thing, but a community thing. So on par with Linux for source, features, performance, everything like that. And ultimately it will be released as an open source project. And the good news is that we have done a lot of work on this, and as you'll see later on the slides, that this is now available for all of you to use and work on and help us actually. The other advantage is common interfaces, so that as long as you keep the DPDK interface the same, any application written for Linux, if it's got to be ported onto Windows, it just works exactly the same way. No changes in the interface. Okay, so the architecture for DPDK on Windows is very similar to what you see on Linux. There's not much of a difference if you broke it down. In user space, you have the application, the libraries, and the poll mode driver. And in the kernel space, you have what is that little component there called the UIO driver. The little difference between Windows and Linux was that on Linux, the UIO driver is built into the kernel. So the IGB UIO driver that the Linux community wrote was just sitting on top of that UIO driver. In Windows, a driver like that does not exist, so we had to write that. And it's not much of a heavy lift of a driver. It's a pretty thin shim kind of driver, just doing the initialization for it. And if you look at the two arrows that go by, you'll see that only on initialization and the resource allocation, we use a UIO driver. And the moment you do that and transition to the fast path, all of data goes directly to the NIC using the poll mode driver. So all of this bypasses all of the kernel network processing in here. So, yeah, like I said in the previous slide, one of the goals was to make everything compile and work on Windows. We did that. We use the Intel C compiler for performance optimizations, and we're looking at other compilers too in the Windows space that we can use. So the code that's available today is building and working with the Intel compiler, but the Intel compiler is not, it's available only as an evaluation release. It's not really free. So if there's anybody else is interested in any of the compilers, please let us know. We'll make sure that the code does compile in it. The UIO driver was in Windows kernel, in Windows, you can only allocate physically contiguous memory in kernel. So that's one of the tasks we had to give to the UIO driver. You can't allocate physically contiguous memory from a user space application. And DPDK, all of the code is based on physically contiguous memory. And like I mentioned earlier, post initialization, the poll mode driver directly sends and receives packets from the NIC. Okay, so what's our current status. So we have performance setup and proof of concept work done that actually works on Windows Server 2016. I believe it's RS1 or 2, I'm not exactly sure. And using the Intel 40 gig NIC, the Fortwell as the code name as I call it, the 700 series 710. We also have an internal demo using the 10 gig Intel adapter, the Niantic. That also works. We've tried that too. We haven't told you guys about that yet. So all the essential DPDK libraries are now compiling. There's I think 37 odd, 36, 37 odd libraries. We have about 32 to 33 of them all compiling and working on Windows now. There are a few that are still stragglers, and new libraries keep coming up, so we got to catch up. So that's why it's important to get us into the mainstream repo so that we don't have to do this. Okay, how did we go about doing this? I missed that sub-bullet there. So the PMD, so the I40 PMD is the one that talks to the NIC. So Microsoft has actually contacted other IHVs now who are now in the process of porting their PMDs to work on their NIC so that they can get everything working with Windows. Porting the PMD was not a hard task at all. Most of the code just works. It just has to be compiled under Windows because it's talking to your hardware. You got to make sure that it works from user space correctly. That's all. So how do we go about doing this? Remember, we wanted to keep the source as much the same as possible as it was in Linux. So one thing we had to avoid was doing a pound-if-def Windows all over the code, because if we had done hundreds of those, when we were going to merge back up into the mainstream repo, the community would not accept it. So we had to absolutely avoid using pound-if-def Windows. But I should tell you that it is not possible to completely avoid it and do it with zero pound-if-def Windows. We had to include some because of some of the ways that the Linux code is written with GCC compiler optimizations. Since we are not using GCC, those compiler extensions don't exist in our compiler, so we had to work around some of those. And some of those GCC extensions are like the ones I said, like type-off is one such thing. There's an equivalent of type-off in the C++ standard, but not in C. So that was something we could not use. And many of these attribute operators, not operators, what are they called? The specifiers, exactly, thank you. So all of those we had to work around. Like I mentioned earlier, we are now investigating C-lang LLVM, and hopefully it gives us a better opportunity than just the Intel compiler. Because again, like I said, the Intel compiler is not available and widely used. I mean, it's available, but not widely used. Okay, and some of the other things was, some of the C standard APIs are obviously supported, but some of the other OS APIs had to be abstracted out using include files. So all of this has been done, and the code that's available up there, Omar will talk about that in one of the few slides going forward. So here's some of the performance setup we did just to make sure that we can match what is seen on Linux. So we had one system running PacketGen, the application that generates packets and can count packets and measure performance. That was running Fedora, and that had one Intel 40 gig NIC in it. We had another Windows Server system that had two 40 gig NICs in it. The reason for using two is so that you can maximize performance, so that you can have one port will do the receive and one port will do the transmit. And if you've seen DPDK, there's this application called L3 forward, which is a very simple application based on some tables. It does some matches and then forwards packets based on what your routing table is. It's a very simple test application. So a packet that's generated from there is sent to this fortwheel here, and then forwarded by the L3 forward application back to the original fortwheel and counted in PacketGen. What happened? Okay, oops, I think I went back too much. So we thought we could show a live demo, but we weren't as brave as Brian was in the morning. So I actually have a video of the demo, and so we did that. Hopefully I can click it here, except I can't see. Oh man, how am I going to do this? Let me see if I can do it here. Yeah, is it playing? Yeah. Can you see it? Yeah. So that is the PacketGen system on the left, and we're just starting up PacketGen there. I don't know if it's very clear back there, but so now PacketGen is started up there. This is a Windows system here. As you can see, it is Windows. So we're going to run the L3 forward application here once PacketGen starts there. So if you look at the command line for L3 forward, all of this is documented on dpdk.org, how to use all these applications. And then now you start PacketGen, enable all of the ports, and ask it to send traffic. And you won't see anything happen here because L3 forward is kind of silent. It just sets up the queues, but it sends the packet back to PacketGen, and you should see the output up there. And if you see the total way up there, the total rate, you can see it's almost 71 million packets, 71.3 million packets a second, which is a line rate for a 40 gig NIC. These are 64-byte packets, so the larger the packet size, the lower the rate will be. Okay. Yes, on this side, this is a Windows Server 2016 system running L3 forward. So, sorry?
You have 4 cores, right?
On this system, I think it was 4 cores. Oh no, it's a 18-core system, but we were using only 4 cores here. Yes.
So, does it come with Windows now, like DPDK?
No, not yet. Well, hopefully we can, right? Yeah. So it's not part of Windows yet. Yeah. So you have to actually download the source from dpdk.org and compile it on Windows if you want to use it today. Omar's got all the details on the slides coming up. So. Okay, and so as you saw, the performance is on par with Linux, and we actually match up on dpdk.org. There's a performance brief that's been posted, and we actually match those numbers for L3 forward. Those are the details of the test system. I believe that was a 22-core system, yeah. And so these are the packet rates that we were seeing, and these match exactly what's seen on Linux. And no, not today.
Yes?
Yeah.
No, Windows has its own built-in switch called
VM switch. Yeah. Okay, and with that, I think I'll hand it back to Omar.
Thank you. Okay. So your driver and patches to make all this work. It's available in the draft repo. Repo name is right there. And it's also been updated to the latest DPDK version that's out there. Thank you, Ranjit. This was fairly recent as of this week. And download it, check it out, install it, try it out, see how it works, give us feedback. If you like it, contribute. If you don't want to contribute, tell us about it. Feature requests, anything you guys might want in this space, we're all ears.
Can you go back a slide as well?
Sure. So all the slides.
We'll be sharing the slides.
The slides will be available. Okay.
That's fine.
So I touched upon this earlier, right? Like in Microsoft, where do we initially expect to use this? And I think this kind of goes to your question, like how would we use this? We have some internal projects around security, traffic generation, sniffing. None of those are really ready to be public yet, but they are, internal use cases where something like DPDK makes a whole lot of sense. Obviously, for our cloud infrastructure workloads, the first step here really is to bring some sort of DPDK functionality onto private cloud, just because that's an area that we can more easily control. And then eventually, something like that could be applicable at public cloud space. Okay? But for now, it would be some kind of a private cloud solution via a software load balancer or a gateway or a similar type of appliance. And of course, we know that there's a lot of interest in the media processing market. That's a market that's predominantly Windows, I would say over 90%. And they're going through a transition right now where they're moving from a proprietary wire technology and protocol over to Ethernet. And they need very high packet processing. And DPDK fits almost perfectly in that space. So we're exploring, okay, what can actually be done here? Our current focus really is, it shouldn't be terminating applications. This would be more like appliance type environments, like everything I mentioned here, including the media processing. NFVs for the cloud infrastructure, those aren't terminating applications. They're effectively, appliances. They're looking at, L3 and L4 and just forwarding it on and doing transpositions. What we are very interested in are scenarios where you bring along your own stack. Like I mentioned before, the applications that are finely tuned to get the absolute maximum network performance with a stack that absolutely fits their needs. So if there's anything in this space that you guys are interested in, please talk to us afterwards or reach out to us. So the DPDK concept, right? So think a poll mode driver, run to completion. You can run it at passive. You run it in user space. It's a great idea. But it could also be applied to kernel space. And we had a similar solution to DPDK in kernel space that is experimental in Windows Server 2016 initial release. This was in 2016. And it's effectively a kernel space poll mode driver, run to completion, runs at passive, has the ability to have interrupts, both time and count based, multi-queuing support, affinitization per VM. All these things are there, but they're experimental. And we went on this path at the same time that DPDK was sort of evolving. And some of this work for Packet Direct was actually in conjunction with Intel early on from several years ago. But we did have some learnings in this, right? Like the DPDK model is very good because you're sitting in user space. It's a greenfield type environment. When you try to apply the same concepts to a brownfield environment, a legacy OS, a legacy kernel, proprietary, that has all kinds of extensible filters that have been there for a super long time, you tend to find things. You find compatibility issues. You find, race conditions. You find all kinds of crazy things. So our experiment with our first version of Packet Direct yielded a whole lot of learnings that we are continuing to invest in. So currently there's a project at Microsoft called NetAdapter, also known as Packet Direct v2. And it's a continuation of everything that was in Packet Direct that operates a whole lot like DPDK, but also addresses all the compatibility and legacy issues that we have to be able to deal with. And it plugs into our battle-hardened, TCP stack that's been around for 20 plus years. Okay? So, in short, which one do you use? If you're going to sit in user space, use DPDK. If you're going to sit in kernel space, hey, or if you're sitting in user space and you require full stack compat and interoperability, then you go with our Packet Direct v2 NetAdapter solution, or legacy NDIS that has a little bit lower performance. So, typical slide, Microsoft now participates in open source. We've got a ridiculous amount of projects in this space. I only listed 3 here, probably the 3 most visible. There's many more that I could list. We expect to be doing a lot of contributions to DPDK as soon as this stuff is up in mainstream. We have a lot of interesting thoughts around the security model for DPDK, namely, the current model really implies that a DPDK consumer is the owner of the device, and he basically owns the entire OS image. So there are concerns that we would have if we ever have the case of bring your own stack on top of DPDK. For example, multi-process, multi-user safety. How do I make sure that one process isn't stepping on another user's memory by programming raw addresses down to the device? So there's a lot of things that we have to consider from a security point of view that we'd like to work with the DPDK community on to improve. And lastly, our roadmap. Everything that Ranjit described in terms of what is currently implemented is really focused on a native device, non-virtualized. A virtual device is effectively the same thing. You just got a shell around it. But there's a lot of things that you have to do to get it to operate in a virtual device. Our first step is to really, once we have a stable, proven native solution, is to do PCI pass-through to a guest, and that guest would be able to use that NIC completely. But eventually, we want to be able to allow for all of this running over a virtual function, combined with a software-mediated data path. So, for example, the difference between Linux and Windows in terms of how NIC devices are presented to guests is that in Windows, a VF is an optional acceleration. It can be removed at any time. And you would always fall back to a software path. So from a VM point of view, you always have connectivity. You don't lose that. So we have to come up with a mechanism to make this work in a DPDK model that's exposed resources up to user space. So if those resources get yanked, there's got to be some intelligence in that DPDK layer to redirect the traffic over a synthetic data path, kernel-mediated I/O and host-mediated I/O out to the fabric and have that work correctly. So we are talking to other folks in the Linux community that are pursuing similar solutions. And with that, questions, comments?
So if you bring your own stack, reliability stack, does it make it easy to move to doctors or microservices, that kind of thing?
I didn't catch the second part, I'm sorry.
Because if you bring your own stack,
Mm-hmm.
does it make it easy for you to switch to microservices or this code?
Yes, it would. Because the traffic would just be redirected in that direction. So what we see is you would have some resources on the device. Those resources could be allocated on behalf of users, and filtering and programming, like some of the earlier presentations today, would allow you to steer the traffic in different directions to different consumers. Now, one thing that I need to make super clear is a BYO stack, as in that should not in any way try to intercept the Windows APIs Otherwise, you get into major compatibility issues, just like you would on any platform. Like if you start intercepting the OS stack's traffic, then you're kind of asking for trouble by doing that. So.
The advantage of bringing your own stack is if your interface below that stack is a DPDK interface, then you can get the acceleration benefits of DPDK, just like that. If today that stack, your stack today is today right into the kernel for the kernel sockets API or some interface, if you can replace that with DPDK, you get multiple X performance.
Right. So for example, if you moved MTCP over to DPDK on Windows, and then you use its socket interfaces, you could have an application talking through MTCP at the same time that you could have another application that's talking to the NIC through kernel space.
Would it mean that you could run multiple stack on the same kernel, on the same machine?
Well, you would run.
You have to pick, you replace an existing one, and you just need to use your new stack. So
that has some overlap with the security model. If I'm assigning a device directly in the standard UIO model, I'm giving the whole thing up to user space. In that case, that device has one and only one stack operating on it. If you have a bifurcated model where you have a NIC that has a set of queues that are given to user space and the other set are going to kernel space, then you can have multiple stacks interacting. If you have a multi-processor safe and multi-user safe DPDK model, meaning that you're using some form of device MMU, so you avoid all kinds of crazy mappings, and you have QoS caps in place, and you can sanitize the type of traffic that's placed on the wire. If you can do those things, then you can have as many stacks as you want that are sitting in user space that are different, because they would be on an application basis.
It's like running multiple VMs, and then simpler way is
True, but yes, it's similar, but in this case, it's not actually a full VM. It's just an application with its own networking stack. So think of it like running multiple networking stacks that may not be the same on the same OS instance.
Yeah. And remember, these stacks are not full-blown stacks. They will be probably very simple. You might have a small UDP or RTP stack, something to that effect. So it is definitely possible to run multiple stacks.
Right. So if you think like an IoT aggregator or gateway, right, and you wanted to build your own stack with your own exotic protocols, then you could do that here, as long as we make it multi-user, multi-process friendly, if that's necessary. Otherwise, you could just be a dedicated VM to do that. Okay? Thank you, everyone.